system properties, description of systems, causal, LTI, and so on, summation of periodic functions, and so on will be applicable when we talk about discrete signals. So we'll talk about description of discrete signals. Let me open the slideshow from current slide. All right, so if you guys remember sampling, I want to reproduce a sequence x of n from a continuous time function x of t in a way that is, I will have samples of this continuous function that will result into a discrete function. So n here is the sample index. It's an integer value, 0, 1, 2, 3, and so on. Ts will be a constant given to you. Well, that's what we call a sampling period or the sampling period. And usually when we do sampling, we do it like in the form of what you call uniform sampling. Uniform sampling means that the space between each consecutive samples is the same. So let's assume this is one sample and this is another sample. So this is space between this point and this point is the same, the space from this point to this point. And that's what we call the sampling period or the time between samples. Now, if there is a fixed time between samples, the sample is called uniform sampling, which is the sampling times are integer multiples of sampling period. Here's an example of a sinusoidal function. So you have it in continuous domain. That's the red line. And the black letter here, or the black font, that's taking the samples of the function at integer points on or integer multiples of t of s. So here the first sample at 0, then the second sample at 1ts, third sample at 2ts, 3ts, and so on, which is the values of n. And then the output sequence would be something like this. Okay, so how to perform sampling? Basically, more into sampling actually will be at the end of the course. But how to perform sampling? Basically, you'll have discontinuous time functions. You multiply it with a train of pulses, and you'll get the amplitude of the function at these points in the time. Now, notice here in function and time domain, the x-axis is t. And the discrete time is n, and here I will have, let's assume this is my 0, this is -1, -2, -3, 1, 2, 3, 4, 5, 6, 7. Sorry, -3 should be here. That's a time index. So those are the values of n, which are integer values. All right, so whatever we did in terms of manipulation in time domain is also applicable in frequency domain, but probably there is this one restriction when we do shrinking. We'll talk about it in a few minutes. Time shifting, pretty basic. If this sign is negative, then shift to the right. If this sign is positive, shift to the left. So here, x of n minus 2, I will shift the sequence to the right by 2 units. And notice here that b should be an integer value. Why? Because my restriction x of n are integer, so I'll be dealing with integer values. So when you have a sequence, something like that, and so on, these values here in the x-axis or n-axis should be integer value, 1, 2, 3, 4, 5. You can never have 4.5 or 4.1. So that's why when you do the shifting should happen as an integer value. If you do a shifting with, let's say, a non-integer value or a float value, it will produce incorrect answer. Basically, you get all zeros because you're taking samples at non-integer indices. Okay, so that's something we already covered. That's an example of time shifting or translation into time domain. So x of n, when you have x of n minus 1, all sequence will be shifted to the right by 1 unit. So here, I started my sequence at -2. It will start at -1 because I shifted to the right. X of n plus 1, then that is a shift to the left by 1 unit. Time reversal, again, whatever we applied in time domain will be applicable also here. So time reversal will be a reflection over the y-axis. And here is an example here. So x of -2 will become x of 2. So the value here will be 1. At 2 will be 1. Similarly, -1, it will become the axis at 1. The value was 1, and you'll get the value here. So geometrically, it's the reflection over the y-axis. or the vertical axis. All right, downsampling, when you multiply with a constant A, so this is what we call a compression. Downsampling, basically, I have the signal of a certain length, 10, and I want to shrink it. Downsampling, like you shrink the signal. One important point here with the downsampling, first of all, A should be a constant larger than 1 to do downsampling. And this result here should be integer. Now, what do we mean by that? Assume that I have y of n equal x of 2n. So I know this is shrinking by half. Like the signal, let's say from 0 to 10, it will become 0 to 5. With this constant, if it's higher than 1, it will shrink. Now, let's assume the sequence or this example here. So I have these samples at -3, -2, -1, and so on. Now I want to have x of 2n. Now someone might say, okay, since I have x of 2n, I will like shrink the function. So all of my x-axis, the n indices, will be divided over 2. So this one here will become -3 over 2, -2 over 2, -1 over 2, 0 over 2, 1 over 2, and so on. So that's the shrinking part. Now, one restriction here is my index here, the result should be integer. Now, when you do -3 over 2, it's -1.5. That's a non-integer value. So this sample will be gone. It will disappear. At -2 over 2, that's a -1. So this sample here that was at -2, it will become the sample at -1. At -1, it will become -1 over 2, -half. This sample will also disappear. At 0 will always remain. This one will disappear. At 2, divide 2, that's 1. This will remain. This one will disappear, and so on. So if you look at the output sequence, I will have at -1, this sample. Notice this one disappeared, this one disappeared, because they will have non-integer indices. They will be eliminated. Again, that's the difference between time domain and discrete domain. In time domain, whatever we have, it will remain there. In discrete domain, the restriction, the result of the indices should be integer. If it's a non-integer value, I will eliminate that component. All right, so at 0, it will remain there. At 1, this sample has disappeared, so there is no amplitude. At 2, 2 over 2, that's 1. So this is the sample of index number 1. Is it clear how to do downsampling in discrete domain? Just make sure that your sequence has integer indices. If you have a value at a non-integer index, just eliminate that value. This sample does not show at the output. Okay, so here is another example here. When you have g of n and g of 2 of n, you will notice that these samples, that they are gone. So this is sample 0, 1, 2, 3, 4. So notice that the odd samples are gone because I'm sampling at 2 of n, 2n. All right, so this is just another example of downsampling, and this is time compression by 2. This one is another sequence. Okay, so you have g of n, that's the original sequence, g of 2 of n, pretty much like the previous example. You're doing shrinking here. Now, when you have g of n over 3, now I'm dividing over a constant, so that's this expansion. Now, what will happen with expansion? My indices, so instead of having 1, 2, 3, 4, I will have 3, 6, 9, like multiples of 3 for this example. In this case, what about the indices in between? They will have 0 value. Like for example here, assuming this is a 0 index, this is index number 1. So when you have g of n over 3, this index will become at 3. So you have 1, 2, and this is index number 3. At 1 and 2, it's zeros. So you just fill the gaps with zeros when you do expansion. With shrinking, you eliminate the non-integer values. With expansion, the gaps, you fill them with zeros. Similar thing here, that's sample number 4, sample number 5, and this is sample number 6, which is equivalent to sample number 2 in this graph. I think that's sample number 2 here somewhere. and so on. So pretty much the same shape, but it expanded. And the samples, I wish they have showed these results here. So this is sample 20, this is 19, that's 21, which corresponds to sample number 7 in the original one. So I believe sample number 7 somewhere there. Alrighty. So 1, 2, 3, 4. Yeah, that's not an accurate actually graph. There's an issue there. Because so this is corresponds to sample number 1, sample number 2, sample number 3, sample number 4, sample number 5. Okay, there's an issue, like these two figures do not align well actually. Because when you have n over 3, so that's the first sample at 3, that's the second sample at 6, that's at 9, at 12, at 15. So when you do it here, so that's sample number 0 at 0, that's sample number 1, sample number 2, sample number 3, sample number 4. Yeah, there is an issue there. Yeah, these two graphs do not align. I need to revise the slide. Revise. To be fair, I'll give you another example different from this one, the whiteboard. Okay, so let's assume that you have this sequence. Okay, let's remove this one. So I have my samples 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. So I have this sequence. Let's assume this is 1, 2, 1, negative 2, 1. These are the values there. So when you have, this is x of n, and I want you to draw y of n equals x of n over 2. So here I'm dividing over 2, so I'm expanding by a factor 2. So my output, you just simply look at the coordinates. So whatever we have, you just multiply by 2. So that's 0, 2, 4, 6, 8. Now at 0, at 0, I have the value 1. At 2, which corresponds to the first sample, I will have the value 2. At 4, I will have 1. At 3, I will have negative 2. And at 8, that's 1. Now, what about the odd samples here? That's 1, 3, 5, and 7. You just fill them with zeros. So that's the expansion part. I hope this one is clear. It's better than the previous figure here, because these two figures do not align well, actually. All right. Slideshow. Current slide. And with the combination, it's pretty much like what we did in the previous lecture when it comes to time domain. Similar thing will be applicable here. So first you apply the time shifting, then you do the whether it was expansion or shrinking, like the multiplication part. All right. Now, even and odd parts of a signal, pretty much the same thing. To get the even part, you sum the function with its inverse, then divide over 2. To get the odd part, you do the subtraction between the function or the sequence with its time reversal version, and then you divide over 2. Okay, so again, pretty much like what we did in the time domain. In the assignment, there is a question on even and odd. In the assignment, have you checked the assignment? No? All right. But yeah, in the assignment, I think there was a question on even and odd. All right. So now when it comes to the summation of periodic sequences, if you remember in time domain, there was a restriction when we do summation of periodic functions that T1 over T2 should satisfy Q over R, if I recall well. That was in the time domain when we deal with the t. Now, when we deal with n sequence, what will be the restriction? Basically, both the period of the newly, let's say, function, let's say y of n equal x1 of n plus x2 of n. The period of y of n will be the least common multiple of the period of x1 of n, like ts of x1 plus ts of x2. Like it will be the summation, the least common multiple of the first sequence period and the second sequence period. So LCM is the least common multiple. Okay, so how to get it? I think that's something you probably did in math, so I'll not spend time on that one. Okay, so sum of periodic sequences for any two periodic sequences, x1 and x2, with fundamental periods n1 and n2. Okay, so n1 and 2. Respectively, the summation of x1 and x2, the period will be the least common multiple of n1 and n2. So let's assume that the first signal has a period of 2, the second sequence has a period of 3. So the summation of sequence 1 and sequence 2 will have a fundamental period of the least common multiple of 2 and 3, which is 6. Okay, so that's about summation of periodic signals. Right-sided signals is a signal that has all values to the right side. Special case, when you have the point is at 0, that's what we call a causal signal. It's the same exact slide from the time domain, but now we are talking about sequences. Left-sided signal has values to the left. If starting with 0, that's what we call an anti-causal signal. And then we have a finite duration sequence that has start and has end. Usually, most of our signals are finite duration signals. And then we have bound signals that does not go over, let's say, to infinity with large values of n. So signal x is said to be bounded if there exists some finite positive real constant, such as the amplitude of the maximum of x of n is less than a. So it does not go to infinity. So that's finite for all values of n. All right. So for example, x of n e to the power 2n u of n, that's not a bounded signal, because with a large value of n, this will go to infinity. Cosine, we already know that cosine does not exceed -1 and 1 for all values of n, so it's going to be bounded. Okay, what about e to the power -n u of n? Is this bounded or not bounded? If you want to draw it, so that's n. At 0, that's the value is going to be 1. At 1 will be something here, e to the power -1, e to the power -2, so something like that. That's what we call an exponential decay. Now, why I started from 0, I have u of n. By the way, I did a mistake. This is a sequence, it's not a function, so I cannot simply draw it this way. I have samples. So decay with all values of time. Again, discrete, I don't have a continuous representation of the function. It should be a discrete value. All right, so that's what bounded signals are. Let's talk about some common signals, sinusoidal and exponents. I think the focus will be on sinusoidals, exponents. I will not spend time on that, but e to the power something alpha, we already know how it looks like. If this alpha is positive, then I will have exponential growth. If this is negative, we have an exponential decay. All right, so for sinusoidals are represented by this expression, a cosine omega n plus phi. Now this one, omega, is like we are used to see like a cosine omega t plus phi. But to differentiate between discrete and continuous, so this is for continuous and this is for discrete. So this one is the angular frequency, which is represented 2 pi f or 2 pi over n. N is the fundamental period of the signal. All right. So, however, there is a condition here that not always the sinusoidals will be periodic in the discrete domain. The condition here to have a periodic sinusoidal, this constant omega over 2 pi should be a rational number. A rational number is represented by integer over integer. So, for example, if you were provided this function sine 3 pi n plus 10, for example, and I ask you, is this periodic or not? So you take this omega, so omega over 2 pi, how much? 3 pi over 2 pi, that's 3 over 2. Is this rational? Yes, then it is periodic. Okay, however, if you are given sine 10n plus 3, always ignore the phase. When it comes to periodic, you just ignore the phase because phase will just tell you that it's a shift between left or right. All right, so you have 10n. This is omega. So I have omega over 2 pi, 10 over 2 pi, 5 over pi. We know this is not a rational number, so in this case, the function is not periodic, or the sequence is not periodic. All right, so in which case the fundamental period is the smallest integer of the form 2 pi k over omega. Okay, something pretty straightforward. Okay, again, just specify just a phase shift. And we know sinusoids are always periodic over 2 pi, multiples of 2 pi of the signal. Okay, exponentials usually represented in this form. Usually we prefer this a to be the Euler number, e. Now, if this value of a is let's say higher than 1, that's going to be exponential growth. If it's less than 1, it's going to be exponential decay. Like a larger, well, it's written here, a larger than 1, that's increase, exponential growth. A less than 1, decrease. If a equals 1, so it's a constant. In this case, it does not depend on the value of n because 1 to the power n equals 1. All right. Yeah, just some information about exponentials. Again, we usually prefer the constant a, which is a kind of 2.7 something. All right, so this is just a representation of the real exponent. So for example, here, when you have absolute value of a larger than 1, so you notice that it's exponentially growing with the increase of the value of n, so exponential growth. So this is an example where you have a equal 5 over 4. C is just a constant, this value here. So it just determines like these values, but the behavior of the exponents is determined by the value of a. Another representation here, when you have a equal 4 over 5, which is 0.8, which is less than 1, and that's you have this decay behavior. All right, and this is a special case where you have a equal 0, so you are raising, a equal 1. So in this case, 1 to the power n, that's going to be 1. So this is just the constant c, and this example c equal 1. Remember in MATLAB, when we want to present discrete time signals, you use the stem command. You've done that in the lab, the stem command, or not yet? Not yet, okay. Here is another example here where you have the value of a negative sign, negative 5 over 4. And you notice that with even indices, you will have a positive value. With odd indices, you'll get a negative value. So basically, when you have like this one, negative 4 over 5 to the power 1, that's negative 4 over 5. So you're getting this value here. Or this is example 5 over 4. 5 over 4, so that's 5 over 4, so that's a negative value. Now at n equal to negative 5 over 4 squared, so it's going to be 25 over 16, and that's going to be positive value. So that's why you notice this alternation of the values of the function, because I have the sign of a less than 0 or a negative sign. Okay. Now, with sinusoids, the general form of periodic sinusoids with this fundamental period N naught is a cosine 2 pi f naught plus phi or omega naught n plus phi. So the relationship 2 pi f naught equal omega naught equal 2 pi over n naught. So keep that in mind. Okay, so unlike continuous time sinusoids, discrete sinusoid is not necessarily periodic. If a sinusoid has a form a cosine f naught, then f naught must be a ratio of integers. I think we talked about it in the previous slides. There you go here, in the real sinusoids. So it should be a rational number or a ratio of integers, if not. Okay, so if f naught rational, the form q over n naught and all common factors in q and n naught have been cancelled, then the fundamental period of the sinusoid n naught, not n naught of q. Again, similar like the example before. So omega naught equal 5 over 6, 5 over 6 pi. So omega naught over 2 pi, 5 pi over 6 over 2 pi. And in this case, pi and pi will cancel. It will be 5 over 12. That's a rational number. So in this case, n naught is 12. So that's how to find the fundamental period. All right, another representation of sinusoids here. So it's just several examples, pretty much like the actual sinusoids that we have. One, again, the condition, 2 pi f naught must be like omega f naught should be rational, or basically omega naught over 2 pi equals f naught, and that should be a rational number. So basically number over number, integer over integer. Okay, we'll talk about the two commonly used functions in real life, the unit impulse and the unit step functions, and from a discrete time point of view as a sequence. So we'll talk about the unit step sequence. Basically, it's the same representation, but instead of having t, I will have n. So it is a signal that has a value of 1 for positive indices of n, and 0 elsewhere. And to draw it, you have the indices 0, 1, 2, 3, and you have just the value 1. Pretty much like the one we do in time domain. You have something like this, and there you go. Then you take these samples, and you have this unit step function. Now, the rectangular pulse, we represented it something like this. And we said, we've seen it a few weeks ago, that how to represent this function as a subtraction of two step functions. For example, if this one is 5 and this one is 10, so to represent it u of t minus 5, so that's going to continuous, minus u of t minus 10, right? Like we said, like this is the shift at the starting point minus the one at the ending point. So that's how to represent that one in time domain. Now, what about in discrete domain? There is a small trick in discrete domain that this index here, you do not eliminate it in that one because you have a sample there. So for example, if I want to represent this one in discrete domain, so I will have samples 5, 6, 7, 8, 9, 10. So that's 5, 6, 7, 8, 9, 10. So that's a discrete representation. Like I took samples from the continuous domain. Now someone might ask, okay, this is going to be simply u of n minus 5 minus u of n minus 10. Okay, now what will be the issue here at the edge here, the sample at n minus 10, if you want to draw it. So you have the subtraction. So that's at 10, 11, 12, 13. I want to eliminate those parts. I don't want to eliminate this one. This one remains there. So I should start my sequence at 11 for this discrete values. So that's how to perform like a rectangular function out of step functions. You do not eliminate the exact, let's say, location at the end. You eliminate the one shifted to the right because I want to retain the sample here. Or if you want, let's do it in more detail in the whiteboard. So let's deal with the shorter sequence. Let's say with a 3 sequence. So that's 3, 4, 5. And I ask you in the exam, represent the sequence as a difference of two step functions. So I'll start with this one. I want to have u of n minus 3. So it's simply a sequence, starts at 3, and it ends at n equal infinity. So that's 3, 4, 5, 6, 7, and so on. 8, and so on. It keeps going. Now, from this sequence, I want to have this one only. Right? I want the 3, 4, and 5. So I need to eliminate this other part here. This one, if you think about it, this is what? U of n minus 6. So to get this sequence, it's going to be u of n minus 3, this complete one, minus this portion here, u of n minus 6. Is it clear? Unlike in time domain, I have a sequence that starts at 3, and I want to eliminate the rest after that. So this sample, there's no sample here. So let's say it's 5, and this is 4. So if I said 6, I will have till 6. No, but in continuous domain, it's going to be u of t minus 3 minus u of t minus 5. So notice the difference between discrete and continuous. In discrete and continuous, I put the exact values. In discrete, no, I have to take account that the last sample is still there. I don't want to eliminate it. Is it clear? All right. So that's how to represent a rectangular sequence, a rectangular pulse, sorry. Unit step function, okay, that's an example. Given the x of n below, represent x of n using unit step function, similar to the example I did before. So that's u of n minus 2 minus u of n minus 5. Always take the sample after. So this one has quite the details there, but this is the answer. It's quite simple. You start from this sample and you eliminate the sample after the one you have. All right, now let's assume in the exam you receive such question, u of 2, u of n plus 4 minus u of n minus n. So there is subtraction. So discard and just copy this question to the whiteboard and try to solve it there. Copy. Okay. So first I need to draw the first sequence and I want to draw the second sequence. Now, u of n is simply starting at 0, and I have these pulses 1, 2, 3, 4, 0, 1, 2, 3, 4, and so on. Now, u of n plus 4, what does that mean? I'm shifting to the left. So I have, now I start at -4, -3, -2, -1, 0, all the way to infinity. Okay, now I just scale it by 2. Now all my amplitudes will become 2. Because initially it's 1. It's a unit step function. That's why they call it a unit step function. It's unit. All right, so I'm done with the first one. Now, u of negative n. So this one is what? Time reversal of the u of n. So this is my u of n, time reversal. Basically, I will have, this is at 0, -1, -2, -3, and so on. At 1, I will have 0. At 2, I will have 0. At 3, I will have 0. So that's u of negative n. Okay. Now the question is asking, find the result of subtracting this sequence from this sequence. The best way to do it, draw a line that has like all combinations of these values. So let's start from, so here I'm starting at -4. And there are values at -4, -5, -6. So I'll start at -6, -5, -4, -3, -2, -1, 0, 1, 2, 3. I can go on, but I think that's more than enough. So that's n. All right, at -6, what was the value there at -6? So -4, -5, -6. So I have here 1. Okay. And what will be the value at -6 here? -5, -6. So it's a 0. 0 minus 1, because that's -6. And this is 1. And I'm having this minus this. So I have 0 minus 1. So that's a -1. So here I'll have this pulse here. At -5, same thing. 0 minus 1, that's -1. Now at -4, 2 minus 1. At -3, I have 2 minus 1. That's another 1. At -2, similarly, it's 1. At -1, that's 1, because what? I'm having 2 minus 1. At 0, 2 minus 1, 1. Now, what about 1? So notice here, like, even though I did not put, this line means that this sequence continues all the way till the end of n, like till whatever value of n. So I have 2. And here, how much I have? 0. 2 minus 0, 2. I'm having this pulse here. What about 2? Same. What about 3? Same. 4? Same. What about 5? Same. So I can do this dashed line, means that this sequence is going to keep going on. What about the values less than -6? So at -7, how much? -7, and I have 1 there. So it's -1. So I can also say this way. It means that the sequence keep going from, so this one is not a time limited signal. It's going to go from -infinity to infinity. U of minus n. Okay, it's a time reversal. So we know U of n starts from 0, 1, 2, 3, 4, all the way to infinity. So U of minus n, that's time reversal. So whatever I have in time will be reversed. Like I have the mirror image over the y-axis. So this one here, whatever, like this is my y-axis, just flip. And I will have the values there. Is it clear? Let me see if the slides agree with my solution. Yeah. Okay. Slideshow from slide. All right. The unit impulse sequence, actually, the good thing about impulse, whatever we did in time domain is the same in frequency domain, sequence domain or discrete domain. An impulse is only a function that has value at n equals 0. and 0 elsewhere. That's it. And represented by delta of n. All right, so the first order difference of u is delta, that is u of n. So this one just saying that to produce a delta function, you just subtract two unit step functions. Now this way, you remember, like it's like creating a rectangle. A rectangle is u of n minus u of n minus 1. You start at 0, you finish at 1. And since we have discrete, I don't have these non-integer values, so I'll have only one sample at n equals 0. All right, an example like a representation of the unit step function, just a summation of pulses at integer values of n. So you have it from, that's u of n, k should be 0 to infinity. That's a better representation. Because the unit step function, u of n, 0, 1, 2, 3, 4. So you start at 0. Delta, this is delta of 0. This is delta of n minus 1, delta of n minus 2, and so on. Okay, a plot of delta is shown below. This one. This is the plot of delta. Just a pulse at n equals 0. Properties of the unit impulse function. That's a property what we call shifting. Shifting property. Basically, when you multiply any sequence with a shifted delta, I'm taking the value of that sequence at that particular shift of delta. Or basically, to have a better representation, assume I have the sequence. Okay, so that's 0, 1, 2, 3. And I multiply it with delta of n minus 1. Delta of n minus 1 is what? It's just a delta at 1, 0, 1, 2, 3. So this is the delta. And the result will be what? This value, x of n minus, sorry, x of 1. As saying that when you multiply the sequence x of n with a shifted version of delta, I'm getting only the value of x of n naught. And this one is optional, actually, this delta, because I'm dealing with discrete. So I'm getting this pulse only, which is basically what? X of n naught. For any sequence x and any integer constant n naught, the following identity holds. There we go. That's x of n naught. That's the same thing here. Now the delta function by trivial is just said like it's an even function. The delta sequence, sorry, the sequence. Yeah, let's not worry about these properties of delta, but most important part, whenever you multiply with a shifted delta, you'll get the value of that sequence at that particular shift. Energy and power. Remember what was the formula of energy? Integration from minus infinity to infinity. Amplitude x of t squared dot dt. And the power limit as t approaches infinity, 1 over t, integration from minus negative t over 2 to t over 2, same expression, x of t squared dot dt, right? You studied for the quiz, so you should remember what that is. Anyways, that's in continuous domain. Now, what about discrete? Now, by definition, what is integration? Okay, no, this one is negative infinity to infinity. But integration, like, what is the meaning of integration? I do remember what is the meaning of integration? When you took in calculus, you're just integrating without the reason why did you do integration? Have you done Riemann summation, whatever, something like that? It is summation. Okay, so in continuous domain is integration, and discrete domain, we will have summation. From n negative infinity to infinity, x of n squared. We don't have dt. That's the energy. Power will be a similar thing, but we'll have instead of T, it's going to be N, I believe. Now let's check the formulas. The energy of the sequence, Ex, N equal from minus infinity to infinity, X of N squared, amplitude. Now, integration was easy, like we've done that in calculus and so on. Now, what about summation? Summation, I'll provide you with the required tables, because you will get some expression, and from the tables, this expression probably is 1 plus n, whatever value it is. Now, energy signals basically means I'm going to square the amplitude because I want to know the magnitude. So negative sign will become positive because I'm doing the amplitude and square it and do the running sum. So that's the energy of the signal. And of course, to have an energy signal, what should be the result of summation? Less than infinity. Because if it goes to infinity, then the signal is not energy signal. Same thing for power. Now, find the signal energy of X of N equal 1/2 to the power N U of N. You're just using the formula X of N squared, N from minus infinity to infinity. Now we have U of N. Like what we did in integration, U of N will what? Eliminate the negative indices. In there, I start my integration from 0 to infinity. Now I start my summation from 0 to infinity. So my summation will become N equals 0 to infinity. Or to put it, let's say in a proper way, N equal negative infinity to infinity 1 over 2 to the power N squared U of N. That will equal the same thing, but from N equals 0 to infinity 1 over 2 to the power N squared. So that's the job of the unit step function. Instead of starting from negative infinity, I start from 0. All right, so my summation becomes like this. One trick here, 1 over 2 equals 2 to the power negative 1. So 1 over 2 to the power n, so 2 to the power negative n squared negative 2n. Okay, and that's going to be 2 to the power negative 2, so 1 over 4 over n. Now in this one, you just refer to the tables. You start from 0 to infinity. So there you go, that's the expression here. And R, the condition, that should be less than 1, which holds here. So in this case, I will have 1 over 1 minus R, and the result will be 4 over 3. Again, this sequence, I think the tables are provided. Okay, I thought they are provided. But anyways, tables will be provided during the exam. And inshallah, before the midterm, we'll do some exercise. Before the midterm, we'll do a session of solving problems. Okay. Find the signal energy of. Now in this one here, I'm limited from 0 to 8. Now 8 is not included, so basically it's going to be from 0 to 7, because here I don't have the equality sign. That's the definition of energy. So the summation is going to be from 0 to 7 again, because I don't have this equality sign. So sample number 8 is not included. Okay, so my summation is going to be from 0 to 7, 5 over 3 to the power 2n squared. Do the algebra. So it's going to be 5 over 3 to the power 4, all to the power n. And there's an expression for that. That's the one. So in this case, n will be what? So n minus 1 equals 7. In this case, n will be 8. Now my expression, since the constant here r, if it's the value 1, then the result of summation is going to be n. However, if it's a different value, I will substitute to this expression. Now the value of n we found to be 8. Now 1 minus r to the power 8. R is 5 over 3. or this one to the power 4. This is the constant r. Okay, and over 1 minus r. So when you do that in the calculator, you'll get this huge number. Again, as long as this value is not infinity, that's an energy signal. So some signals have infinite, like the rationale of why looking for the power signal. Some signals, they have infinite energy, like the cosine and sine, sinusoidals, because they go over, let's say, all time. So we were looking for the average power. So in that case, it's usually more convenient to deal with the average signal power. So the average power, its limit from n equal to infinity, 1 over 2n, summation from negative n to n minus 1, x of n squared amplitude. That is the expression. Then you substitute the value of n, and again, do the algebra, familiarize yourself with the summations. So for periodic signal x of n, the average signal power is given, like that's a special case when you have a periodic signal or a periodic sequence x of n, the power will become this expression. So the notation summation of n over n means that the sum over any set of consecutive n's exactly n length. So like you're taking just a single period, not the whole sequence. Okay, signal with finite energy, we call it energy signal. A signal with infinite signal energy and finite power, we call it a power signal. So here is an example. Let x of n be a signal with x of n equals 0 for n to negative 2 and n larger than 4. So my signal is bounded from negative 1 to 3. Again, I don't have the equality signs. So my signal is bounded from negative 1 to 3. Now, for each signal given below, determine the value of n, which is guaranteed to be 0. Actually, this is not related to energy and power. Just here, shifted to the right. So here, then my signal initially is from negative 1 to 3. Okay, so shift to the right by 3 units. It's going to start from 2 and end at 6. That's the first question. Second one here, shift to the left by 4. Initially at negative 1, shift by 4 to the left, negative 5 to negative 2. Negative n, time reversal. Initially it was negative 1 to 3, then it become negative 3 to 1. Time reversal. Okay. X of n. All right, determine whether or not each of the following signals is periodic. Let's just look here. Signal x of n equals 0 for n less than negative 2. Okay, let's focus on this question a little bit. It's saying that the signal x of n equals 0 for n less than negative 2. So this is the negative 2. Less than that will become 0 at negative 3. So at 2 there is a value. Okay, my bad. I think I interpreted the question wrong. So when you have it like this, x of n equals 0 for n less than negative 2, it means negative 2 has value. Okay, you see the point? I was confused a little bit here. So at negative 2, it has value, and at 4, it has value. Okay, so my limits is going to be from negative 2 to 4. Now the same applied, negative 3. So shift to the right by 3. So it's going to be 1 to 7. N plus 3 to the left, negative 6 to 0. And this one from negative 4 to 2. Determine whether or not each of the following signals is periodic. What do you think this one? Is it periodic? Just draw it. Now, how to draw this sequence? U of n plus u of negative n minus 1. So x of n, u of n plus u of negative n minus 1. Check. Okay. So U of n, we'll just simply draw it. So that's a 0, 1, 2, 3, 4, and the value is 1 at all. Now, what about U of negative n minus 1? How to do it? What do we do first? Shift to the right. Okay, so shift to the right by 1. So 1, 2, 3, 4, that's U of n minus 1. Then to get U of negative n minus 1.
It's going to be from -1.
So now that's time reversal. -2, -3, -4, and so on. That's 0, 1, and 2. Okay. Now you are adding this one to this one. So is there any overlap? By overlap, like, do we have like common indices? Let's say add 0, this one, add 0. So basically I'm taking this image and I put it there. So I'm gonna have this sequence. So from -4, -3, -2, -1, 0, 1. So this part here is the U of negative n minus 1. And this part here, that's the U of n. What do you think? Is this one periodic or not? Okay, what do we mean by periodic? Does it repeat itself? Is there a sample that repeats itself here? Yeah, like it's just a pulse that's repeated all over n. So the result here is periodic. Okay, even though initially we said, oh, it's U of n, it's not periodic, etc., whatever, but the result of adding these two sequences was periodic. All right, and the fundamental period is 1 U of n plus U of negative n. Similar to this one, but I'm not doing the shifting. So basically, I will have, let's say at 0, I will have a pulse. So the result of the output, I will have 2 here when we do the addition. There's overlap at n equals 0. And in this case, the signal or the sequence is not periodic anymore. Clear? Okay, from current slide. Display settings. Okay, last slide. For each signal given below, determine all the values of independent variable at which the even part of the signal is guaranteed to be 0. And by the way, my questions in the exam will be straightforward. This one is playing with the words. What do you mean, like the even part is 0? Then the signal is what? La. La. Okay. So we said like all of the sequences x of n is x even of n plus x odd of n, صح? Like all signals are composition of even and odd. Now, if I said even is 0, what will be the signal? Odd signal. So for each signal given below, determine all the values of an independent variable at which the even part of the signal is guaranteed to be 0. So I need to find the odd part of this function. Okay, so in this case, you have the function there, U of n minus U of n of n minus 4. How to find the odd part? X odd of n, 1 over 2, x of n minus x of negative n, and that's it. All right, so let's look at this function. Let's draw it. U of n minus U of n minus 4, I know it's going to be what? How many pulses? 4 at 0, 1, 2, 3. So that's my original sequence. That's x of n. By the way, when you have this expression, don't apply the formulas to u of n and u negative. It will become very complicated. Just look at the drawing, then apply this time reversal to the drawing. It will be way easier. All right. So I have this drawing here. That's x of n. Now x of negative n. So this is 0, 1, 2, 3. X of negative n be negative 3, negative 2, negative 1, 0, 1, 2. So I'll have the pulses there at the negative indices and zeros elsewhere. Add them together. I will have it like this. So at 0, I have this overlap, 1 and 1, I will have 2, and 1s elsewhere. Then divide by 2. So this is 1, this is half, half, half. And that's it, that's the odd part. Is it clear? That's it for this lecture. I know it went a little bit quick, but there are a lot of similar ideas from the continuous domain concept. And inshallah, next week, actually, there will be more material to discuss. Stop recording. Stop.